as a reminder, the 8th problem set is due Friday. I probably haven't fixed that on the website. It's definitely Friday. A lot of it's about lenses and things like that. And I haven't mentioned in class that the simulations that exist for a handful of the topics, there's a simulation for cameras. At the end of the section on cameras in the ebook, if you go all the way to the bottom, you'll find a camera with a flower and lens and an imaging screen or sensor, and you can drag the flower around, you can drag the lens around, and you can change the focal lengths. Basically, you can sort of experimentally solve a number of the questions on the problem set, playing with this simulation. So I encourage you to do that. All right? Otherwise, we're back to nuclear weapons. And the story I'm trying to convey is sort of the structure of the nucleus and where its energy is. Again, nuclei of atoms are made up of what are called nucleons, which consist of, they're two members of the nucleon family that are significant here, protons and neutrons. Protons are electrically charged positive, one fundamental positive charge. The neutrons are electrically neutral. It turns out a neutron by itself, it has a little larger mass than a proton, and if you just leave a neutron to itself, it decays spontaneously. That is, eventually it breaks into pieces. And the pieces it breaks into, oddly enough, are a proton, which is positively charged. To conserve electric charge, you can't just make positive charge out of nothing. So the neutron breaks into a proton and an electron, and one other particle that balances another issue in physics in the universe. It breaks into a particle known as an antineutrino, which is, okay, it exists, it's there. Anyway, the neutron breaks up into three pieces, one of which is a proton, one of which is an electron, and one of which whizzes off, almost undetectable particle. What else is here? Okay, so neutrons are stable when they're in nuclei, or at least in some nuclei. So the point is that when you assemble, in this case, 11 protons, 12 neutrons together into one object, which is ultimately it's a quantum mechanical object, so it's got wave character to it too, and I've drawn it as little balls, but it's okay. And that is the nucleus of a sodium atom. And it's stable despite the fact that the protons hate each other, want to spread out. They would love to just head off to the four corners of the universe. They're stuck by the nuclear force, which is a short-range force, something new to us. That the force of gravity goes on forever. The force of electromagnetic forces go on forever. The nuclear force doesn't. It's short-range. It only reaches a tiny bit outside of a nucleon, and sort of holds them within a Fermi or so of each other. Remember, Fermi is this tiny distance. It's 10 to the minus 15 meters. So they're stuck together by that. And if you think in terms of you think of the process of assembling this nucleus. You bring in positive charges that repel each other, and as you do, the voltage goes up, right? So you're doing work on them, pushing them together. They would fly apart as soon as you let go of them if it weren't for the nuclear force, which grabs them eventually when they touch. And a way of thinking about that process of bringing this together is like rolling a ball up a hill. You have to push it the whole way up the hill until it reaches the top, and then there's a little dip. Imagine that something's carved out a little well in the middle of the top of the hill. And so you push a ball up the hill, and if you let go anywhere along the path and let go, it will release its gravitational potential energy. But no, you carry it all the way to the top of the hill and let it roll into that little dip. And in that last bit of rolling into the dip, it actually releases energy. You can now have a little bit of work done on you as you let it go down into that dip. And it will sit there. And in the classical world, that is the world before relativity, but also mostly before quantum mechanics, that ball would sit there forever. It would never, even though it was chock full of gravitational potential energy that could be released if it could get to the well, get out of the well and get to the main slope of the hill and roll down miles and miles. It can't. It's stuck in that little well. If you smack it hard enough, you can give it the energy it needs to get up to the top of the ledge and then roll down. But without that energy, it's never going to get out. So that may not seem like it's directly connected with the idea of assembling these particles into a nucleus, but it's very closely related. So as you bring them together, you're doing work on them, and if you let go anywhere along the assembly process, they'll fly apart. But no, you actually let them touch, pull together with that special short-range force, which is like rolling down into the well, and then they sit there. And classically, they would sit there forever. All right. A few details about the structure of that analogous hill and dip. For the giant nuclei, the hill, like uranium is a nucleus with 92 protons. That defines the chemical, the element uranium, because 92 proton nucleus will attract 92 electrons, which gives the chemistry of uranium. But so that giant nucleus, bringing those 92 positive charges together was a heroic feat. It was ultimately done in an exploding star long, long ago. And there was a huge amount of work done in bringing them together. And then they are pulled together and held there by the nuclear force. So there's that little well at the top where they sort of ran into the dip, and they're sitting there. They've been sitting there for billions of years. Okay, but if they could get out of that well, whoa, they would release this huge energy that was invested in bringing the positive charges together. So this is a case in the giant nuclei. There is most of the energy that's relevant is the repulsion between the positive charges, the electrostatic potential energy there. In the tiny nuclei, such as helium and lithium and hydrogen is too, but all those little nuclei that's at the beginning of the periodic chart with only a few protons in their nuclei. It turns out the nuclear force, the repulsion, invested energy in the repulsion isn't all that big. So, yeah, you have to push them together, but once they get close and stick, that sticking process, the well that they roll into as they stick, actually does more work on you than you invested pushing the positive charges together. So you can actually get a net release of energy by assembling those nuclei, the little guys, out of smaller pieces. That's a process known as fusion, and fusing nuclei together that releases energy. That's the basis, as we'll see, for thermonuclear weapons, hydrogen bombs. So assembling small nuclei actually releases energy. Disassembling large nuclei releases energy. That's a process called, among other things, fission. And that's the basis for the uranium and plutonium bombs. I can talk about these things as though they're just no big deal, but and I've gotten flack for doing so. They're not a big. They are a big deal, as you well know. A couple of years ago, I visited Hiroshima. It's a pretty somber place. So, I can tell you about these things. Hopefully you'll never encounter them in your lifetime in any effective situation. But okay, so back to this. It turns out you can release energy assembling little nuclei into bigger ones. That's the process of fusion. That's the power source in the sun. And it finally can be used for other things. And you can release energy by disassembling the big ones, like uranium and plutonium. So how do you disassemble them? Well, I've talked about that one. Okay, so why are some nuclei unstable? It turns out that not only is it possible to disassemble some of them disassemble themselves in an amazingly random way. And so that randomness is worth dwelling on for a little while. When you bring together 92 protons, by themselves, 92 protons will not stick and stay together for any length of time. The repulsion is so fantastic that they just simply blast apart. So you have to dilute them with something that experiences the nuclear attractive force, but not the repulsive electrostatic force. They're diluted with neutrons. So the point, in a uranium, there are two existing forms of uranium nuclei. One of them is known as 235 because it's got 235 nucleons in it, and one of them is known as 238 because it's got 238 nucleons in it. 92 of those, in each case, are protons because that defines the element. You're okay with the idea that the number of protons gives you the element because it attracts an equal number of electrons, which gives you the chemistry of the element and it defines it chemically, which is how we define elements. Uranium is different from its nearest neighbor, neptunium, because neptunium has 93 electrons and a subtly different chemistry than uranium. All right? So uranium, the two normally existing uranium, they're called isotopes because they differ only in the number of neutrons they have. They have the same number of protons, therefore the same chemistries. Uranium-235 has 143 neutrons in it. 143 neutrons, way more than the protons. Their job is basically to dilute those nasty protons so they don't repel each other as ferociously. Let them get farther apart. And uranium-238, which is actually even more stable, has 200. Should be able to do this better, faster in my head. 238 has 146 neutrons in it, and the rest protons. Okay? So they're known as isotopes of uranium. Again, they differ only in the number of neutrons. They're chemically indistinguishable. They have a little difference in mass, and that makes this is a huge deal, ultimately. They're very hard to separate from one another because they are chemically equivalent. The only way, you basically have to shake them. Are you the heavy guy or the light guy? Heavy guy, 238. All right? Both of those nuclei turn out to be radioactive. What's that mean? It means that when you assemble them, classically, here's my hill story. Here's the classical one. You push all the particles together. It's like going up the hill. And yeah, you got multiple balls you're rolling up the hill now, and which is pushing on which, it turns out not to be very important. The detail is you're pushing you can maybe even think of the last proton. You push up the hill, it gets to the lip, and it rolls down to the bottom, and it's happy. This downhill roll was the nuclear force pulling inward and doing work on you instead of the other way around. Is that okay with everybody? Classically, it would sit there forever. What's it going to do? It's a ball sitting at the bottom of a well. It's going to be there tomorrow. Quantum mechanically, it's not really a ball. It's a wave. These are all standing waves in the nucleus again. And a way to think about that system sitting in the bottom of the well, again, you got lots of balls attached to each other. How is that like one ball sitting in a well? Well, physicists like to do analogies, and this analogy is perfectly good. It's like a single ball sitting in the bottom of a single well, and if you could get out of that well, which you could if you gave it a good kick, you'd get it up the hill, whoa, and then it would roll down. That would do it. But alternatively, just let it sit there and recognize that it's not truly a classical billiard ball particle. It's a wave. It's a standing wave, and it has enough energy it's happily in that well. It wants to sit there, but waves don't cut off abruptly in normal situations. So this location at the bottom of the well has a certain amount of energy, and it does not have enough energy. I mean, let's look at the classical one again. This ball has enough energy to be at the bottom of the well. It does not have enough energy to be on this lip. That would require somebody to give it some energy, do work on it, push it up the hill. The wave, however, can actually have some extent into that barrier. Physicists think of this as a barrier preventing the ball from leaving, and it's an energy barrier, meaning you can't cross it without enough energy. But the ball as a wave can actually be in the barrier. Not much of it. Not much of the wave is in the barrier, but not zero of it. A little tiny bit of the wave is in the barrier. And if you go looking for the ball, remember these kinds of stories, you go looking for the ball, you disturb it. Well, if you go looking in the barrier every minute, is it in the barrier? Is it in the barrier? If you do find it in the barrier, it will have enough energy to be in the barrier. And the act of looking will have invested the energy that it was missing to get in the barrier. All right? If you just leave it alone, it can be in the barrier without having to prove that it has enough energy. This is one of these Heisenberg uncertainty principle things. Like, if the time is very short, it can have, the energy is not very well defined. You cannot know how much energy something has and know about it right now. You have to watch its energy for a while to have it become well defined. If you look very quickly, you'll get fuzziness to the energy. And so here again, too, it's kind of, don't catch me. I'm in the barrier. I'm in the barrier. It keeps doing this kind of thing. As long as it's brief, it doesn't have to keep the energy well defined. So it keeps looking. If you look, you'll find it you might conceivably find it in the barrier, in which case the act of looking, of the energy needed to make the measurement in that will have paid off, will have paid the price of the missing energy. So in these two uranium isotope nuclei, the wave character is in the barrier. It's very, very weak there. But there is a chance as time goes on, and if you leave it, you do have to leave it alone. If you keep looking for it and keep finding it in the middle, it won't ever escape. But if you leave it alone, the wave may eventually evolve in a way that allows it to escape from the barrier. Actually, it travels continuously across as a wave and gets to the edge, at which point, once it's outside this edge, it no longer needs the energy to go over the barrier. It's gotten to this far side. It can actually just simply roll downhill. So it can escape from the barrier as a wave tunneling. It's called tunneling through the barrier. It doesn't go over the barrier the way it would if you bumped it. It's simply that the wave doesn't cut off abruptly at the barrier. It has some amplitude in the barrier and all the way out. And that connects on to the possibility of it simply escaping altogether on the far side. It's kind of a crazy thing. This is one of these quantum mechanical things that they probably told you that if you run against the wall often enough, you eventually might somehow go through it. Sort of. That's kind of taking it a little bit far. But for subatomic particles to tunnel through barriers, this sort of thing happens all the time. I told you last time, I believe, about flash memory, the famous flash memory that stores all the permanent code on your cell phone. You might carry around everything you've ever seen or written about on a little thing like this. What's the memory in there? The memory is charge on little isolated gates on MOSFETs. And those insulated gates that you can't get at, you have to be able to put charge on and off them eventually. Otherwise, you can't change it. You can't write anything. So how do you get charge into it? Tunneling. This same process. You get it to go through a region where it's not classically allowed because it can't actually be in there without extra energy. You can get it to sneak through by way of quantum tunneling. All right? So what does quantum tunneling get for you? It means that in the case of these uranium nuclei, you let them sit around for a little while, like 5 billion years. They run a decent chance of having tunneled through the barrier. The wave tunneled through the barrier, escaped, and the thing flew apart into pieces. That's natural radioactivity. It's a completely random effect in a way that's sort of unfathomable. I mean, actually, just before I forget, these little toys have the same physics, the classical version of the same physics. There's a spring and a suction cup. The spring is like the long-range repulsive force, like the electrostatic repulsion, bringing it together. You have to do work to close the spring, and then the short-range force, namely the suction cup, grabs onto the little guy. And it sits there, and these guys will, they're classically stable, but these guys, I didn't know, this was a toy when I was a kid. They still make this thing. They just sit there and they eventually pop sort of semi-randomly because the suction cup's got a leak. They deliberately make it flaky. Okay, so the guys leak. Of course, the kids quickly learn which suction cups let go faster than the others because the goal is to catch the guys when they jump. But that's classical. It's a classical physics scheme for them to get past that barrier. Quantum mechanics allows it to happen. Even with a non-leaky suction cup, in principle, these guys would eventually tunnel past the suction cup and jump. In real life, that would take 5 million universe times. It would never happen, for practical purposes. But in little nuclei, it happens. Because it's completely random, what does that mean? It means that every day that goes by that a uranium nucleus did not explode, it has exactly the same chance in the next day of exploding. It does not accumulate any tendency to go off. You all know that if you play the lottery, suppose you go play the lottery every day. You go in there and you put in the same number just because you do, because you're compulsive about it. Put the same number in. And there's a natural human tendency to go, I lost, this is the 37th day in a row that it lost. It's getting more likely that I'll win next time. Is it really getting more likely that you'll win next time just because you played the same number and we'll do it again? No. There is no accumulated anything. There's no memory in the whole system. Bingo's a different game. If you're waiting for B3 to show up and it hasn't shown up in, 74 picks, it's going to show up the next time because the statistics are evolving. There's no evolution in the statistics of radioactivity. Every day a nucleus survives is another day behind it. The future is completely unpredictable nonetheless. All right? And if any of you who do play the lottery thinking that that you're getting more and more chance every time you lose, clean slate every time, no memory. So you end up with what's called a half-life in these totally random systems where it's like rolling the dice. I don't want to zap too much time here, but I'll zap a little time on it. If you look at this document camera, I'll put it in the center just because I can. But a bunch of dice. And let's say every time I'm going to roll the dice, every time a 1 comes up, that's that dice exploding. So it's got a 1 in 6 chance of going every time I roll it. I pick them up, I go shake, 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 roll. And now all the 1s, kill them off. They exploded. The 1s are gone. Got them. Okay? So the first time, of course, we lost a lot of dice. Second time, nope, a bunch more went. I cheated on a 1, but I don't think it was a, okay. Third time, I'm now down to about half the original dice. So it takes about 3 rolls to wipe out about half the dice. And if I keep going, oops, didn't lose any that time. Lost this one, try again. There, lost 2. It's going to taper off. And this will actually be an exponential decay. If I did it with enough dice, I've got enough, but no one's got patience to do this. If you do it and keep rolling, you'll find this beautiful exponential decay. It follows the exponential function with e to the minus time over something. And it will slowly decay off, and if you've got enough dice, eventually you'll run out of dice, but if you've got millions and millions and billions of dice, it'll still keep tapering. People like to define what's called a half-life for, in this case, dice, but in other cases it may be nuclei. Half-life is the time it takes for half of the original crop of nuclei to have exploded. And so you've only got half as many. And the half-life for uranium-235 is something under 1 billion years. And the half-life for 238 is something considerably over 1 billion years. I just never remember the numbers exactly. But they both have very long half-lives. But uranium-235 has a shorter one. And so while they were probably both roughly equally abundant way back when the star formed them, the uranium-235 has dwindled to something under 1% of the existing uranium. The vast majority of uranium nuclei are the slower to decay ones, uranium-238. Is that okay? There are nuclei with half-lives measured in billions of years. I mean, there's some that are simply stable, never explode. Then there are ones with nuclei that decay in billions of years. I don't know whether anything goes longer than billions of years that's known. But there are also ones that go in weeks, minutes, seconds. It all depends on the electrostatic repulsion, the neutrons, complicated issues, and also how they decay. There are different ways of decaying. They can throw off a little piece. They can split in half. It's a whole variety pack. All right? So that's the background for, I guess, for nuclear weapons. I told you about, large nuclei have two ways that they can get in trouble. Too many protons, there's just too much repulsion. Too many neutrons is also a problem for them. Yeah, it dilutes out the protons, which is good, but then the neutrons get lonely, and they run the risk of, like an isolated neutron, falling apart into pieces, those pieces being a proton, an electron, and an antineutrino. So you got to get the right balance between them. And there are only two versions in uranium that have decent lifetimes. There are some other ones that you can make synthetically, other uranium isotopes, but they don't live very long. So they didn't survive since the Earth was formed. All right. Yeah. Just before going on to chain reactions, let me just show you some of the things that are around that are radioactive. I got started on this last time, and let me just show you some more. So this is a device that looks basically for the shrapnel that comes off of certain radioactive decays. The different pieces that come flying off, some of them are easier to detect than others. This one detects a certain class of pieces. And as I said last time, a certain type of Vistaware that was made with this specific orange glaze. That's a uranium-based glaze. I don't know whether uranium is... Can you buy uranium? You may need licensing to buy uranium stuff. This, you can still buy uranium stuff. You just get it on eBay. But that chirping, each one of those is a decay. So there are hundreds, millions, thousands per second coming off this guy. It's quite radioactive. But if you remember, Avogadro's number is a big number. So the number of uranium nuclei here is huge. 10 to the 20th, 10 to the 18th, something like that. So losing a million of them a second is no big deal. Okay, another thing that's radioactive. Long ago, luminescent washes that would glow in the dark. They still make washes that glow in the dark, but you have to expose them to light to make them glow. They store the energy and they release it as glow-in-the-dark stuff. This has a little bit of radium in it. So that was kind of a rare thing. There was an era when they would deliberately put radioactive stuff into the phosphorescent paint so it would glow even without exposure to light. So this has got radium in it, and it's nice and hot. The sad story with that is that the people who painted the dials got sick. And the worst part was they would tip their brushes in their mouth, and so it would just destroy their mouth. The one thing that I know of that you can still get that still has a radioactive component in it is the mantles for gas-powered lanterns, camping lanterns. They still sell them anymore. Light bulbs have taken over everything, or LEDs. But at least you used to be able to get a lantern that would operate on propane or on gasoline. And the mantle, the best mantle material that you would get hot and it would glow with thermal radiation, the best mantle material was a ceramic. And it was a ceramic that contained thorium. So thorium oxide was you'd buy the mantle as it is now as a fabric, and you would burn the mantle, and the thorium would burn and become an oxide mantle. And thorium made a great mantle, but it is radioactive. And finally, we're radioactive to some small extent, primarily because potassium, one of the potassium isotopes, is a radioactive isotope. Potassium 39 probably, or 40, I can't remember which one. Anyway, it falls apart and becomes argon, an argon nucleus. And potassium's everywhere. You eat a banana. So it's mildly radioactive. And we do fine with modest amounts of radioactivity around. A lot, not so good. Okay? One other thing to show you, and to do that, I'm going to get rid of those guys. I will put the spark chamber over there. And I'll go back to the computer. And I'll put the spark chamber. You're now zooming in on this guy, this thing here. That has little wires that when I turn on the power supply and turn up the voltage, will make sparks. If something ionizes the air between the little wires and a plate, a spark will occur, because there's a very large voltage there, very large electric field, but there are no charged particles in there, or very few. If you can create a little track of charged particles, you can make a path for movement of electric charge, and a spark will develop. So this will detect radioactive stuff by creating a spark. This is actually how a lot of the fancy detectors for particle physics experiments are based on this concept. Basically, a radioactive decay that shoots shrapnel through the air in the vicinity of one of those high voltage wires will trigger a spark. So what am I going to use as the source? Smoke detectors. A lot of smoke detectors use a little piece of americium, which is a transuranium element. It's an element that's got even more protons than uranium. So it's not naturally occurring. It was made in a reactor somewhere. And they use that to actually charge passing dust particles so they can detect smoke. Can you see on the screen behind me the sparks? Yeah, it's even better if I shadow it. It's spark, 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 woo! Okay, so that's another one of those rare things that's radioactive that you can buy. That is smoke detectors. They have this little radioactive source inside. All right. Any questions about radioactive stuff? It's completely different from like microwaves. People confuse, like, is a microwave oven going to make me radioactive? Completely separate worlds. The microwaves, they're essentially low frequency radio waves. Well, they're high frequency radio waves, but they're low frequency on the electromagnetic spectrum. The photon energy, the energy per quantum in a microwave is teeny tiny. It can't do anything. So apart from heating you up, it's kind of innocuous. The energies associated with the things that come flying out of radioactive stuff, much larger amounts of energy in the single quanta of things flying around. So they can do all kinds of stuff, like the particles coming out of that americium were knocking the electrons off of dozens or hundreds of air molecules as they flew by, just knocking the bejeebers out of stuff. So it's much more energetic. So, all right. So that's the story of radioactive stuff. Okay, so how does a nuclear chain reaction work? In this case, if you start with one exploding nucleus, or the particles from similar, when they hit another nucleus, they can knock it out of its fat and happy sitting in the well situation. They can knock it over the edge and cause it to fly apart. So they can induce breakage. So it's not, natural radioactivity is sit around, wait for it to go spontaneously. Induced effects are ones where you smack the nucleus and make it change. And some nuclei, not all of them can do this. Actually, relatively few can break into semi-equal pieces. Uranium-235 is one of those. It by itself, just sitting there minding its own business, can occasionally break, not by sending off a little piece, but rather cracking in half, like you hit the egg on the edge of the bowl, bam, and both halves go off. So that's called fission, when the nucleus breaks into semi-equal chunks. And you can, not only can 235 fission spontaneously, it can be caused to fission by hitting it. It undergoes fission if you smack it with it, for example, with a projectile that can sneak up on it and crack it. And the projectile that has the easiest time sneaking up on any nucleus, it's not a proton. Protons are repelled. So a nucleus knows a proton's coming. Whoa, we feel this repulsive field coming at us. And they actually will slow it down gradually, and it won't hit so much as bounce. But a neutron, nobody knew it was coming until it hits. It's a neutral thing. So neutrons tend to fragment. They're the most effective breakers of nuclei. And a nucleus can come into uranium-235 and smack it and crack it into fragments. And the fragments that fly off often are semi-equal in size, but they may well include smaller shrapnel and other neutrons. So breaking a uranium-235 nucleus can cause it to shatter, a process which releases a huge amount of electrostatic potential energy, and it can send off shrapnel that includes additional neutrons, which can shatter other uranium-235 nuclei and cause the same thing to happen again and again, and you can get what are called chain reactions. So this is a picture of just one of these induced fission events. A neutron snuck up. Let me get this back to normal. See myself giant size over my own shoulder. Come on. There we go. Okay, so this is one neutron sneaking up on a uranium-235 nucleus. It hits. Even if it's traveling relatively slowly, it still hits because it's sucked in at the last minute by the nuclear force. In it goes, it smacks that guy, and it busts apart, and out comes pieces, which include neutrons. And those pieces, incidentally, are the nuclei of existing elements, but they typically have more neutrons than they should for being as small as they now are. They're overrich in neutrons. So a lot of the debris created by this process includes elements that are familiar, but weird versions thereof because they got more neutrons than they deserve or want. And I'll talk about fallout later. So, I'm going to skip this because we're all tired. Okay, so here's the idea of a chain reaction. One neutron comes in, blasts apart one of the uranium-235 nuclei. Out comes shrapnel, and includes neutrons which blast apart other uranium-235s, which more shrapnel, blast apart more. You get this ongoing process of one fission begets at least one additional fission. And if it turns out that actually happens, that you start with one fission and things are arranged such that you get more than one subsequent fission, which gets more than one times, you keep getting more. So with each generation of fissions, there's a first generation which is a single nucleus breaking. There's a second generation, which is the shrapnel from that first generation breaking more nuclei, which creates shrapnel and causes a third generation and so on. If with each generation you get more and more fissions, it's a chain reaction that is growing and therefore explosive. Actually, so that's the explosive character of a chain reaction. If with each generation you get fewer and fewer and fewer fissions, it fizzles out. After generation 12, maybe you're down to no fissions. So you can get growing, which has an exponential character to it getting bigger, and you get an exponential getting weaker. Once people figured out, neutrons hitting some of these special fissionable nuclei causes them to break and send out more neutrons, which causes more. we can make a runaway thing. They immediately realized two things. They realized, well, this is a tremendous energy source because all that energy is stored in these nuclei by the exploding star way back when. We can release that energy and do good things with it, like power the universe, power the world. And then other people thought, wow, if we do that in a short period of time, we're going to make some incredible bomb. So naturally, the bomb came first. And to do that, you needed only a few things, really, conceptually. You needed the first neutron. So you need something that breaks the first nucleus. You needed a material that is fissionable. That is, when you hit it, it breaks into shrapnel that includes neutrons. And you need each fission, it has to release more of these fission-inducing neutrons. And the material has to use the neutrons efficiently so that each generation is larger than the previous generation. And this efficient use of neutrons defines what's called the critical mass. It's not literally a mass. It's more a matter of efficiency. If you have a very small amount of one of these fissionable materials and you throw the first neutron in, it may well fracture something and out will come neutrons. But if too many of the neutrons simply get out of this little volume of space before they have a chance to break stuff, the chain reaction will fizzle out. So the larger the material you're dealing with is, the higher the chance that any given neutron will hit something before it leaks out. So more mass actually does matter. Bigger masses are more likely to go crazy and explode. Denser materials also, the more tightly packed those nuclei are, the more likely it is for a neutron to hit one before it sneaks out. So starting with a material that's got a medium density and smushing it, which you amazingly enough can do with high explosives, you can pack a material like a chunk of metal, like, just to pick one at random, plutonium-238, 239. Smush that together and double its density. So it was meant to be a grapefruit-sized chunk of plutonium ordinary sitting there minding its own business. You smush it with high explosives to much smaller. You make an orange out of it. Its density went way up. It uses its neutrons more efficiently. It explodes. Okay? So the two, for this sort of nuclear weapons come in two variations. One of them is the fission bombs, which are based on giant nuclei. And the fusion bombs, which are based on, they start with fission bombs as an energy source to get things started, and then they use little nuclei. All these are relevant at the moment with North Korea. Uranium-235 and plutonium-239, both of them are fissionable nuclei. If you get a whole lot of those guys together, enough of them packed tightly enough, and you throw in the first neutron, kablamo. About obtaining them, uranium-235 is very rare. Uranium-238, as I'll talk about when I talk about nuclear power, uranium-238 is much more abundant. It has lots of energy stored in it, but it doesn't fission. If you hit it with a neutron, it does something weird. It gobbles up the neutron, says thank you very much, and it then undergoes a series of internal rearrangements. The neutrons are getting lonely, and the neutron explodes and becomes a proton, an electron, an antineutrino. The element changes to neptunium. This happens a second time, and it becomes plutonium. And so uranium-238 evolves into plutonium-239. That's the story for the future. But uranium-235 naturally occurring is fissionable. Plutonium-239, if you can get, is also fissionable. So to get uranium-235 by itself, you have to use its mass to separate it. So this is during the World War II. There was this heroic effort to separate something like 60 kilograms, the first nuclear weapon. The Hiroshima bomb was a uranium bomb, and they separated, I think it's 60 kilograms of uranium-235. So it was an object like this, but it took huge resources to do it. the bomb used in Nagasaki was plutonium-based. It was obtained with nuclear reactors in this country, I think all in this country, turning uranium-238 into plutonium-239. Plutonium-239 is a distinct chemical, different from uranium, and therefore separable using chemical processes. So they separated out the plutonium and made a nuclear weapon out of it. So the first nuclear explosion was the one at Trinity site in Alamogordo, New Mexico. That was an experiment where they really didn't know whether it would work because it was a bomb based on plutonium. And they really wanted to test this first before they dropped a really whopping dud on Japan. So they set this up. It was a 6 kilograms of plutonium, so a little ball of plutonium, and they crushed it with high explosives. And so they took its density from normal to something like twice or whatever, its normal density with high explosives. And that act of shrinking it like that took it above critical mass. So prior to that, it was a nasty radioactive mess. You wouldn't want to be near this sucker. But it wasn't undergoing this growing sequence of fissions. Once they crushed it, one fission generation, it sort of doubled. Each fission generation was twice as big as the previous one. And the time between generations was something like 10 billionths of a second, 10 nanoseconds. So in some fraction of a microsecond, after they crushed this thing, some significant fraction of the nuclei inside blew apart. And it was a tremendous explosion, of course. They did the same thing on Nagasaki. Okay? The bomb dropped on Hiroshima was a different concept that they knew would work. Uranium-235 is less radioactive by far than plutonium-239. Plutonium-239 is so radioactive, it's got a half-life of like 25,000 years. So the nuclei are just popping like right and left. Plutonium is so radioactive that they didn't think they could assemble the bomb in pieces. They had to have it start as a ball and crush it. The uranium bomb, they could assemble it. And what they did was they made a sphere that had a cylinder missing from it. And without the cylinder, it was below critical mass. With the cylinder, it was above critical mass. And they shot the cylinder in with a cannon. So the bomb there was a long, thin guy that had a cannon inside it that fired with normal explosives, fired the missing cylinder into the sphere, completed it, and that process took enough time that they were sure that there would be at least one radioactive decay would trigger the event. So at some point in its path into the cylinder, the first neutron came in, triggered the first fission, and the whole thing ran away. Huge chain reaction and giant explosion. All right? With that, we can do our less destructive chain reaction, because it's fun. So here we have who wants to trigger the chain reaction? Daniel, you get to do it. So here are the nuclei sitting here, each of which is going to be able to toss out 2 neutrons. They're all ready to go. Your job is to drop the first neutron into... Oh, okay. Thanks. Setting that up is no fun because it's, you never know when it's going to blow. All right. So it's the same idea of chain reaction that one explosion of the mousetrap tosses out multiple neutrons that trigger more, which trigger more, which trigger more, and runs away. All right. We'll continue on Friday.